When a physical object arcs through the air, its trajectory never rests. It climbs, decelerates, peaks, and falls, operating under a shifting rate of change. This creates an immediate mathematical problem. Most of the early systems we study are linear, meaning they change at a locked, predictable speed. This linear graph, y equals mx plus c, has an identical slope anywhere. Introduce an x squared term, and the line bends, fracturing that uniform speed. A single quadratic curve contains infinite slopes, steep positive on the left, flat at the peak, and negative on the right. The analytical challenge is pinning down a reliable mathematical method to measure a rate that refuses to hold still. If we can calculate that dynamic rate at any given instant, we can identify the absolute mathematical peak or floor of any modeled system. This data table evaluates the simplest quadratic function, y equals x squared. As the inputs advance in standard single steps from negative to positive 2, the squared outputs jump, first by -3, then -1, +1, and +3. These jumps are called secant lines. They act as rigid bridges measuring the average rate of change between exact coordinates. If we isolate the segment between x equals 1 and 2, the slope of this secant line is exactly 3. To find the true slope of the parabola, we look to the horizontal midpoint. At exactly x equals 1.5, a tangent line sits perfectly parallel to our secant line, sharing that exact slope of 3. Multiply 1.5 by 2, you get 3. This 2-to-1 relationship holds across the entire curve. At the midpoint of 0.5, we see a slope of 1. At -1.5, we see a slope of -3. In every instance, the instantaneous rate of change is exactly 2 times the value of x. We have replaced approximation with geometric deduction. By utilizing these midpoints, we can lock down the exact rate of change at any single instant without guesswork. This table expands that logic to the general quadratic equation, ax squared plus bx plus c. The output differences now become complex algebraic expressions. Notice the constant c. When calculating the actual difference between points, c subtracts away entirely. It only dictates the vertical starting position, so it has zero effect on the slope. By applying our midpoint geometry to the remaining variables, the algebra simplifies down to a single universal rule. The instantaneous slope of any quadratic curve is 2ax plus b. We can test this derived formula against a live economic optimization problem. A regional transportation company operates with a base fare of 40 rupees and serves 500 daily riders. The company needs to increase revenue, but market data proves a harsh constraint. Every 4 rupee hike in the fare will drive away exactly 10 riders. This equation models their total profit. We multiply the shifting rider count, 500 minus 10x, by the shifting fare, which is 40 plus 4x. Expanding the binomials reveals the underlying function, -40x squared plus 1600x plus 20,000. The a coefficient here is -40. That negative value dictates the physical shape of the data, forcing the parabola to open downwards. Because the structural curve points downward, the company's profit has an absolute peak ceiling. Our dynamic slope formula is designed to expose exactly where it is. Finding that exact peak without manually calculating every single potential price hike requires us to look at the rate of change. This graph charts the profit function. As the price hikes increase, profit climbs the left side of the curve. But notice the tangent line. As it climbs, the positive rate of change shrinks. At the absolute maximum, the vertex, the tangent line stops climbing completely and locks into a perfectly horizontal position. A perfectly horizontal line represents a rate of change of exactly 0. This allows us to isolate the peak algebraically. We set our derived slope to 0, subtract b, and divide by 2a. That simple manipulation leaves us with x equals -b over 2a. This proves exactly where a system's rate of change halts and reverses. We can drop the bus company's variables right into the formula. -1600 divided by 2 times -40 outputs exactly 20. Translating that algebraic output back to reality, the optimal business strategy is exactly 20 price hikes of 4 rupees each, pushing the total fare to 120 rupees. Inputting that 20 back into the profit function locks in our vertex coordinates. The absolute maximum profit yield is exactly 36,000 rupees. Compared to their starting baseline of 20,000 rupees, That is an 80% increase in total revenue, realized solely by solving for the exact peak of the curve. Finding that vertex is like reaching the exact physical summit of a mountain. Once the slope hits zero, there is no higher ground to find. By learning to track a shifting algebraic rate of change to exactly zero, we isolated the point where growth halts and the downward curve begins. We deduced the mathematical framework of optimization and laid the direct conceptual foundation for differential calculus.